Longest common subsequence. Longest common subsequence problem is a classic problem in algorithms that can be solved using dynamic programming. The problem is about finding the longest subsequence that is common to two sequences. If you have sequence 1 and sequence 2, you have to identify the longest subsequence that is common to S1 and S2. Then the question is, what is a subsequence? This is a bit different from the concept of a substring. A subsequence is a sequence that appears in the same relative order but not necessarily contiguously. If it is a substring, it has to be in contiguous order, but if it is a subsequence, it may or may not be contiguous. Let us understand this by taking an example. If you have a string, the CS underdog, this is the string you are having, CS underdog. Let us try to find out which are the subsequences of the CS underdog. We told you have to follow the order that is from left to right, but it need not be contiguous. You can choose any letters. You need not necessarily choose contiguous letters. For example, TES. TES is a subsequence of the string, the CS underdog. Similarly, if you choose CNE. So CNE is also a subsequence of the string, the CS underdog. You can also pick contiguous letters. For example, if you pick DOG, dog is a subsequence of the string, the CS underdog, as well as a substring of the string, the CS underdog. So here, dog is a subsequence as well as a substring. But in case of TES and CNE, these are not substrings. These are only subsequences because they are not contiguously present in the original string. This is the difference. Next question is, how are you going to find out which are the common subsequences, and then how are you going to find out the longest common subsequence? The simplest approach is you can take sequence S1, find out all the possible subsequences of sequence S1, then take S2, find out all the possible subsequences of S2, and then keep comparing each of those and find out which are the common subsequences, and then identify the longest among all of those. This is a very hectic process and we are not going to do this. What are we going to do? We are going to use dynamic programming. In order to reach dynamic programming, what we'll do is, we'll first start with recurrence relation. We'll try to understand what is the recurrence relation we should form in order to find out the solution for this, and then we'll see how is dynamic programming introduced in order to make it more efficient. This is the best way to understand this problem. Okay? Now, what is the problem statement for us? The problem statement is you have a string X. So let us say X is the first string. It is having X1, X2, X3 up to, let us say, up to XM. So what are these X1, X2, X3? Those are each letters T, H, E, C. These are X1, X2, X3 and so on. So totally it is up to XM. We'll have one more string Y. This will be having Y1, Y2, Y3, so on up to Yn. So these are the two strings we are having. What is the task? We have to identify the longest common subsequence among X and Y. This is the final task. What is the length of X here? Length of X is M and length of Y is N, because X is from X1, X2 up to XM, which means its length is M. Let us try to write recursive relation for this. What is the core of recursion? You have a larger problem from where you are starting. What will you do? You will split it into smaller problems and make recursive calls on both of those. Again, on those smaller problems, you'll again make recursive calls. Like this, you're going to break it into smaller problems, solve recursion, and when it returns back, you will finally have the final solution. This is how generally recursion works. So let us try to write the larger problem in terms of some smaller problems. This is how recursive approach should be taken. What is a recurrence relation here? LCS, the longest common subsequence of what are the factors here? One is X, which is our first string. The other string is Y. Then what are the lengths of X and Y? M and N. These are the factors that we want to consider. Using these factors, if a parent problem can be called as LCS of X, Y, M, N, then what are the smaller problems that we can break this into? This is what we want to understand. So think about this. We have two strings. One is X, one is Y. What should be the smaller problems so that the larger problem of identifying the longest common subsequence, which is called as LCS of X, Y, M, N, can be resolved? We'll see it like this. What is the base case? The simplest case is, what if either of the strings is 0? Let us say string X is of length 0. That is, there is nothing in string X. X is a simple null string. If it is a null string, then there is no subsequence for this null string at all. Because it is not having any subsequence, there cannot be any common subsequence with any other string. Because of which, either X or Y, if any of them is 0, in that case, your LCS will be 0. So basically, with this problem, we are trying to find out the length of LCS and not exactly LCS. See, we'll find out LCS. We'll finally get into what exactly is the LCS of this problem. But for now, we are looking at finding the length of LCS. So how do we identify the length of LCS? This is the first thing we are going to tackle. Once we tackle this, once we understand how to use DP approach to find the length of LCS, we can easily backtrack and find out what exactly is the actual longest common subsequence. Okay. So this is the approach. LCS is 0 when, what is the case? Either if M is equal to 0, M is equal to 0, or if N is equal to 0. What happens with if M or N equal to 0? This means length of X is 0. This means length of Y is 0. If either of them is having a length of 0, that means the longest common subsequence is having length 0. This is the base case. Let us get into the tougher cases. Next cases, there are two more cases remaining. One is if two letters of these two sequences match. And the second case is in case two letters don't match. Let us take two strings. Let us say you have one string A, B, C, D and another string which is A, B, D. If this is the second string. In this case, you will start from the last letter. What are you going to see? You are going to see whether the last letters of both these sequences are they matching. In case they are matching, what is the advantage for you? The advantage is you know that a subsequence of the string will be having D as the last letter because D is common. So D can be the last letter. The remaining letters that are part of the longest common subsequence that have to be identified by using the remaining parts of both these strings. So you are clear that one letter in the subsequence is D. So how can you identify this? How can you represent this using recursive formula? You can say the length of your LCS, it is increased. You can count at least this particular one into the length of LCS. So LCS will be 1 plus LCS of remaining. What is LCS of remaining? Remaining part is your X is remaining as a string, Y is remaining as a string, but length of both X and Y is now M minus 1. Why is it M minus 1? Because the last letter is already consumed. Using that, you added this 1 to the length of LCS, which means now you are having the remaining part of both the strings. So with remaining part of both the strings, you are going to find out the same problem. LCS problem, you are going to call the same problem on the remaining part of string. Whatever be the longest common subsequence possible from the remaining part of string, to that you can simply add 1 and say this is the LCS of the larger string. This is the idea. So here it will be M minus 1, M minus 1 and N minus 1. So this is your LCS problem that is newly defined using recursive formula. When is this done? This is done when x of m is equal to, that is the last letter of x is equal to y of m. Whatever be the last letter, if that matches, in that case you can write 1 plus LCS of the remaining strings. That is removing the last letter, whatever is remaining in both the strings, you will take those and try to find LCS. Next one is the tricky one. In the next case, what if these are not matching? Let us say instead of D, this was D and this was E. In this case, the letters are not matching, so you can't simply add 1. In that case, what do you have to do? This is the tricky part. Here, the trick is, you already know that the last one is not matching. So, you have two options. One is, you have to see the longest common subsequence between the whole string x and this part of y. This is one option. And the other option is, you have to take whole string y and this part of x. Why am I doing this? The reason is, last two, whichever be the last ones, they are not matching, which means you don't have a common subsequence from here. This is for sure. What is the next best thing? You have to try if it is possible to have a common subsequence by taking one less letters from the first string and all the letters from the second string. This is one possibility. Other possibility is take one less letters from the second string and all letters from the first string. Is this possible? You have to see either of these possibilities. Why are you doing this? Because you already know if you take all the letters from both and see the last ones, there is no possibility at all because these two are different. So this is what you are exploring. What should be the recursive relation here? You have to find maximum of, what are the two things? First thing is LCS of, you have to remove one from the first and then one from the second. So if you remove one from the first one, it will become LCS of x, y, then m will become m minus 1 because you removed one letter, and n will stay as it is because you are using the complete one. And then what is the second one? Second one is LCS of x, y, m will stay as it is. And for the second string, you will have one letter less. That is, you will take n minus 1. Among these, whichever is the maximum, whether it is LCS of x, y, m minus 1n or LCS of x, y, m, n minus 1, whichever is the maximum, that is the count you are going to take as LCS of the largest string. Okay. So what is the case? This is done. Okay. Here I'll write if so that you understand this is the condition. Similarly, this is done if x of m, what happens if these are not matching? So this is not equal to y of n. In this case, you are going to see both of these. So at this point, we are clear with how to solve the problem. So you know that if you use this recursive formula, you are 100% going to get the right answer. This is for sure. So at this point, you have one logic or one algorithm in order to find out the longest common subsequence. But there is a problem. What is the problem here? The problem is, if you actually do this by using this recursive relation, let us see how long it will take to reach an answer. The problem is you have x and y, and let us say x is having a lot of letters. Let us say A, B, C, 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 D, something like this. This is your string x. Here, for each of the entry in x, you are having two choices. That is what you are doing here. For each of the entry, what are you doing? In case that letter is present or in case that letter is not present in the LCS. Both conditions you are exploring. Which means for each of the letters in the x or in case of y, you can take whichever. In either cases, for each of the letter, you are exploring two possibilities. Which are the two possibilities? The possibilities are this letter is part of the LCS and the second possibility is this letter is not a part of LCS. You are exploring both the possibilities, which means corresponding to each of the letter, you are giving two options each in order to identify whether this is the actual LCS or it is not the actual LCS. That is, if the total length of the string is m, then you are having a total of order of 2 power m steps, which means this is exponential. What is the total time complexity of this solution? Total time complexity will be order of 2 power whichever is minimum among m and n. So this is a very large time complexity considering it is exponential. Whenever your time complexity is exponential, you have to realize that you need to check for a better solution. Exponential time complexity is never feasible. Why is it not feasible? The reason is, as the input size increases, your total time taken will increase exponentially. So it will go out of control. This is why recursive solution is a very good solution for this problem. You'll get the right answer, but it is very time consuming. Time complexity is very high. This is a very time consuming solution. What do you have to do now? You have to identify some way of decreasing the time. What is the way of decreasing the time here? Let us look into this and see where are you losing time. Okay, this is what we have to understand. First thing, I already told you there are a total of order of 2 power n steps here. Let us understand where are the 2 power n steps coming from. If you see each of the problem has to say LCS of, you have x and y which are constants. Then you have all possibilities for m from 0 to m, and for n you have all possibilities from 0 to n. If you have all the possibilities from 0 to m, that means there are m different possibilities for the size of x. Similarly, there are n different possibilities for the size of y. If you think again, you will understand that if there are m different possibilities for size of x and n different possibilities of size of y, then the total possible problems that you have here, total possible recursive calls that are possible here are totally m into n. So mn is the total number of recursive calls possible. When I say number, I meant total different recursive calls. Total number of calls, we already said it is 2 power n. But I'm saying you possible different or independent recursive calls are m into n, which means how is it reaching order of 2 power n? It is reaching order of 2 power n because it is continuously calling the same call repeatedly. This is what we understood. How did we understand? Because total number of different recursive calls is order of m into n, but we know we are having total of 2 power n or 2 power m number of recursive calls. How is this possible? The only possibility is many of these recursive calls are being made multiple times. So you are repeatedly calling the same problem. This is when you have to think about dynamic programming. Whenever you know there are multiple calls or repeated calls on the same problem, same recursive function on the same input. If this is happening, you know, because there are repetitive calls, what can you do? You can use dynamic programming. What are you going to do in dynamic programming? You will have a table in dynamic programming. You will store all the values in the table. And whenever you make the same recursive call again, same recursive function with the same input, whenever that call is made, you are not going to solve it anymore. You are simply going to fetch it from the table. What will this do? This will decrease the total time complexity because you are no more going to make recursive calls on that. So let us understand how can we apply dynamic programming approach here. So in dynamic programming, we are going to use the tabulation approach. That is bottom-up approach for dynamic programming. We'll see which is the smallest possible sub-problem. From there, we'll start solving this. So in order to do the same solution, so the reason I wrote this recursive solution is we are going to use the same logic and I am going to convert it into dynamic programming. I want you to understand what is the recursive relation here and how exactly I'm going to convert this into a dynamic programming problem. If you understand this conversion, you'll be good to solve any dynamic programming problem. Otherwise, you'll keep thinking dynamic programming is something very difficult. Okay, you have to understand that it is simple recursion, just that you're storing the value somewhere. Okay, so here we are going to use a table for tabulation. Let us see what are the steps followed. You'll easily understand this. First step, what is the first step? You have to create a two-dimensional table. So you want a 2D table or a matrix. We'll call it DP table. DP of what should be the size? It should be of size m plus 1 cross n plus 1. This should be the size of your DP table. Why should it be m plus 1 cross n plus 1? Because we already discussed total number of different recursive calls made is m into n. If this is the total number of recursive call, in order to store that, you need m into n different blocks. That is what you are having here. And why is it m plus 1 and n plus 1? That is because first row and first column will be having all zeros. This is why we are having this. You'll understand why it is when we go forward. So this is the DP table. Next thing you have to understand is, what does each block in this DP table represent? Any block, let us say DP of ij. What is this particular block going to represent? See, whenever you are learning any dynamic programming problem, try to understand it in the same order. If you understand all these particular components of dynamic programming, you'll easily understand the concept. So dpij, this particular block will represent LCS, the longest common subsequence of x from 0 till I minus 1. That is, in the x string, if you consider only the letters till the I minus 1th letter, and from the y string, you consider only the letters till j minus 1. So if you are only considering these many letters, let me write it here, y from 0 to j minus 1. If you are considering only first I letters of x and only first j letters of y, then what is the longest common subsequence length possible? That is what dp of ij will represent. In this matrix dp, any particular block dp ij will represent what is the longest common subsequence possible if x is only having first I letters of x and y is only having first j letters of y. This is the basic idea. Then the next thing is, you have to initialize. What is the second step? You have to initialize with all zeros in the table. So you need not make all zeros. Instead, you can just make first row as 0 and first column as 0. This should do. Why is first column and first row 0? We already said each block represents LCS when x is having only first I letters and y is having only first j letters. What is the first column? That represents the 0th column. That is, x is having 0 letters. If one string is having 0 letters, length of LCS is 0. That is why we are having first row as 0. Similarly, first column is 0 for the other string. So this is the case, base case, when either of the strings are having 0 length. What is the next step? Third step is, you have to fill the table using recurrence relation. So here you have to fill the table, and while filling the table, we'll be using the recurrence relation that we learned here. We'll see how it is done. We'll write this separately, okay? After this, what is the final step? Let us say you fill the complete table. You fill the complete DP table. Starting from the beginning, you fill the complete table. Then whatever is the answer in the final block, that is your final LCS of the complete problem. That is dp of mn. Whatever is the value present in the final block of your dynamic programming table, that will be your answer. Why is it? Because that represent LCS when x is having all letters and y is having all letters. That is why that particular block represent the LCS. So let us try to understand how to fill the table. What is the rule used to fill the table? I want you to keep this in mind, whatever recurrence relation we had written, we are going to convert this into matrix form in order to fill the table. So instead of this recurrence relation, I am going to write it as matrix. That is, instead of recurrence, we'll be trying to fill blocks of the matrix. So how should I fill? I want to fill some particular block. Let us say dp of ij. This is the block I want to fill. While filling this, what should I see? What are the different cases possible? One is I'll fill 0 if, what is the case? If either I is equal to 0 or j is equal to 0. If either I or j equal to 0, that represents the base case here, m equal to 0 or n equal to 0. In that case, you will be filling with 0. This is the base case. What is the next case? Next case is, we said if the last letters match, then you will do 1 plus LCS of the remaining string. That is the logic we use here. When we convert the same thing into matrix form, what happens? It will be, this can be written as 1 plus dp of, instead of ij, you have to decrease one letter and go backward. That is I minus 1, j minus 1. This is how you can write. What is the case? This is the case when ith letters match. So ith letter can be written as x of I minus 1 equal to y of j minus 1. So this means ith letter of x is matching with the jth letter of y. Then what can you do? You can write dpij as 1 plus dp I minus 1 j minus 1. So this case is clear. What is the next case? Next case is, in case the last letters do not match, what do? You take the maximum of two possibilities. One possibility is if the first string is having one letter less and the second string is having complete letters, and the other possibility is first string is having the complete string and the second string is having one letter less. Let us write this in matrix form. So when you write this in matrix form, it will become maximum of, what are the two things? One is dp of, here you have to decrease one, so I minus 1, and for the second string you will consider whole string I minus 1 j, and what is the second possibility? It will be dp of I j minus 1. Here the first string is having all the letters, and for the second string you are having one letter less. So this is in case if x of I minus 1 is not equal to y of j minus 1. So this is a basic way of solving it. Now you would have understood why I wrote recursive relation first, because this is the recursive relation from which we got the idea of how to solve. We implemented the same idea using dynamic programming in a matrix form. So this is the logic we have to use in dynamic programming. And most important part is, let us understand how did time complexity come down. Previously I told you time complexity was order of 2 power minimum of m and n. This was the time complexity. Let us see what is the time complexity if you use this solution. In this solution, you are trying to fill each of the block in dp. In order to fill each block, what is the total work done? If it is 0, you are simply writing 0, which means order of 1 work. What if it is last letters are same? If x I minus 1 equal to y of j minus 1, in that case, you are simply fetching value from one particular block and adding 1 to it. So this is also order of one time operation. What is the other case? In case the letters do not match, then also you are simply looking into two blocks inside the matrix and you are simply finding whichever is the largest. This is also order of one operation, which means total number of operations that you have to do is to fill each of the block, which is order of m into n, because there are a total of m into n blocks. That is the size of your table. So the total work done is filling each of the block, and while filling any single block, you are doing only order of one work. So the total time taken is only order of m into n, order of m into n, is the total time taken. So you can clearly see when we changed from the recursive approach to the pure dynamic programming approach, we were able to decrease the time complexity from order of 2 power m to order of m into n. So from that exponential time complexity, we brought it down to m into n. What is the space complexity here? Space complexity comes from the additional table we are using, that is also order of m into n. So both the time complexity and space complexity in this case is order of m into n. I want to do one more thing in this lecture. In the next lecture, we'll go to complete illustration of this. We'll take an example and illustrate how exactly each entry is filled in the table. This lecture, I want to show you a pseudocode so that if you want to actually write a code for this problem, you should not face any challenges there. That is, you know this is the logic, but how exactly will the code look like? So I want to clarify this part as well. What I'll do is, I'll just erase something from here. Is it okay if I erase this part? I'll erase these things from here. You anyway have the recursive relation. You can refer to that recursive relation that we wrote on top. So I'm going to erase this thing and we'll write pseudocode here. This is erased. Let us come with the pseudocode. So for the pseudocode, these are the steps to be followed. First thing is you want a 2D table. So I'll write the function as LCS of x and y. X and y are the strings. In the string, what is m? M is the length of x. M is length of x. Similarly, what is n? N is length of y. These are the two initial parameters that you want. What is the next thing? The next thing is, what are the steps here? Step is to have a 2D table dp m plus 1 cross n plus 1. So the next step is to have a table. This is a dp table. This will be m plus 1 cross n plus 1 table. So initialize the table. It should be having all zeros. It is not necessarily all zeros. If you simply have the first column and the first row as zeros, that should be good enough. You need not have all zeros. I'm just writing all zeros here for simplicity. Then the next thing is you have to start loop. In the loop, what should be the logic? The logic should be what we wrote in this recurrence relation or what we saw in the matrix form. So we are going to use the matrix form, but the base is recurrence relation only. So in the first loop, you should go through each of the entry from 0 to m. So for I is equal to 0 is already filled because you have all zeros. So I equal to 1 to m. 1 to m for all blocks. While you are iterating through each, what should you do? That is, you have a table. In this table, you have I here 0, 1, 2 up to m. And here you have 0, 1, 2 up to n. So for each of the entry, let us say you are at 1. You have to go through each entry in the table and fill it. So for 1 to m, you have to loop through 1 to n. For j is equal to 1 to n. For each of the entry, what should you do here? You should fill the matrix. While filling the matrix, what is to be taken care? You have to see for two possibilities. One is if the ith and jth entries match, then there is one possibility. If it does not match, we have to use the other recurrence relation. So what should the first one be? In case if what happens? X of I minus 1 is equal to y of j minus 1. If the last letters match, then what should you do? Your dp, what did we write just now? Your dp of ij, how do you identify this? This should be 1 plus dp of I minus 1, that is one letter less in x and one letter less in y. So j minus 1. This is in case the last letter matched. If it doesn't match, then what? Else. So ideally, I just want to write an else case here, but I'll write else if so that you will clearly see what is the condition here. Else if x of I minus 1 is not equal to y of j minus 1. In this case, what will you do? In this case, you want to find maximum of two things. Which are those two things? Your dp of ij, this will be maximum of, first thing is, in case in the first string there is one letter less, dp of I minus 1 and j. And the other cases, in the second string you will consider one letter less, that is dp of I j minus 1. These are the two possibilities. From these two, whichever is the maximum, that will be filled in dp of ij. So with this, your algorithm is done. Finally, you have to return whichever is the entry in the last block. So return dp of mn. That is whichever is the entry in your last block. You have the dp table. You kept filling all the entries. Whenever you get the entry in the last block, that is your final LCS count. Let us see this algorithm once more just to be clear. What did we do here? LCS. In this we found m and n, which are the lengths of x and y. We initialized our dp matrix m plus 1 cross n plus 1 matrix into all zeros. What did we do then? We started looping through each row in the matrix. For each of the row, you have to go through entry in each of the column in the matrix. What do you do there? For that corresponding entry, that particular value of I and j, you'll see whether the ith value in x and jth value in y, are they matching. In case they are matching, you will say 1 plus whatever is the value of I minus 1 and j minus 1. That is what you will have as the present LCS. In case they do not match, you have to find the maximum among the value which is having one letter less in x or one letter less in y. Whichever is the maximum, that is what you're going to take. Whatever be the entry in the last entry of your dp table, that is the length of your longest common subsequence. So this is the algorithm that can be used to find out longest common subsequence. In the next lecture, it's an important lecture where we are going to see how exactly each entry is filled in the dp table by taking an example. We'll take two strings as example and understand for those strings, if you want to identify the longest common subsequence, how exactly each entry is filled. Once you understand that, the whole picture will be crystal clear for you.